So let's talk about one of the most important steps in all of data science, model validation. This is the part that takes a really complex algorithm from being just a fancy guess and turns it into a tool you can actually trust to solve real problems. Let's dive in.
Okay, imagine someone hands you a machine learning model, and they tell you it can predict almost anything. What movie you're going to love next, or even if a bank should approve a loan. That sounds amazing, right? But everything, and I mean everything, hangs on one single question. Should you actually trust it? How do you know it works and isn't just, making stuff up?
The best way to think about this is like a student who's cramming for a huge exam. They could just memorize the exact answers to the practice questions, right? And if you give them those same questions again, they'll get a perfect score. But did they actually learn the subject? Nope. A machine learning model is exactly the same. It can totally memorize the data you show it, but that doesn't mean it's learned a single useful thing.
And that right there is what we call the A-plus student problem. It's this tricky situation where a model looks absolutely perfect on paper, but is really just set up to fail spectacularly the second it sees something new. This usually happens when the model is just way too complex, and instead of learning the big picture, it starts memorizing every little random detail from the data it was trained on.
So here's the thing you really need to get. A model that gets a 100% score on its training data, that's not a success story. That's a huge red flag. It probably means the model just memorized the answers, and the moment you show it some new data it's never seen before, it's going to fall flat on its face.
So how do we fix this? How do we actually make sure our model has learned something real? Well, the solution is actually pretty simple, and it's basically the golden rule of all machine learning. You can't test a student on the same questions you gave them to practice with. You need a final exam.
In the world of data science, we create that final exam using a technique called the train-test split. And it's pretty much what it sounds like. We take all of our data and we split it into two piles. One pile is for training, that's the study guide. The other pile, which is kept completely separate, is for testing. That's the final exam the model has absolutely never seen before.
And the process itself is super simple, but it is absolutely crucial. First, you start with all your data. Then you shuffle it all up, kind of like a deck of cards, just to make sure there's no weird order or bias in there. After that, you slice off a big chunk for the model to learn from. That's your training set. And finally, you take that smaller piece and you lock it away. That's the test set, and the model doesn't get to see it until the very end.
Now, a really common way to do this, a sort of industry standard, is a 75-25 split. You use 75% of your data to teach the model, and then you hold back that other 25% for the final test. This gives the model plenty of information to learn from, but still leaves a pretty big chunk of unseen data to really prove it knows its stuff.
Okay, so our model's been trained and it just took its final exam using that test data. So now what? How do we grade it? Well, first let's look at what are called classification models. These are the models that sort things into different buckets or categories.
So for a model that's just making a yes or no decision, like is this email spam or is this customer going to cancel, you might think, hey, let's just see what percentage it got right. But it's not quite that simple, because sometimes how the model is wrong is just as important as when it's right.
This is where something called a confusion matrix comes in handy. It sounds complicated, but it's really just a simple scorecard that breaks down the model's performance. True positives and true negatives are easy. That's when the model got it right. The really interesting parts are the mistakes. A false positive is when the model predicted yes, but the real answer was no, like a legit email getting sent to your spam folder. And a false negative is the opposite. It predicted no when it was yes, like a really nasty phishing email landing right in your main inbox. See? Different kinds of wrong matter differently.
Now, using those numbers from the confusion matrix, we can calculate the most basic metric of all, accuracy. This is pretty straightforward. It just tells us, out of all the predictions the model made, what percentage did it get right. It's a good starting point, kind of like getting your overall percentage on a test.
But of course, that's just one way to grade a model. What if your model isn't predicting a category, but a number, like the price of a house or what the temperature will be tomorrow? That's called a regression model. And for that, we need a totally different grading system.
For regression, one of the most important scores is called R-squared. Now, you can ignore that complicated definition for a second because the idea is actually pretty simple. It's a score between 0 and 1, and it just tells you how well your model's predictions line up with the actual real-world data. A score of 1 is a perfect fit. A score of 0 means your model is completely useless, no better than just guessing the average every single time.
And this quote from our source material really just nails it. A low R-squared score means your model's predictions are, well, they're all over the place. They aren't following the actual trend in the data at all. A high R-squared, on the other hand, means its predictions are clustering really tightly around the real values. It's a great fit.
So, we've talked about splitting up data, confusion matrices, R-squared, a lot of technical stuff. But why does any of this really matter? What's the big picture here?
At the end of the day, validation is everything. It is the only proof we have that a model has actually learned a pattern, not just memorized data points. It's what builds trust. Without this step, we'd be letting flawed or even dangerous algorithms out into the real world. It's the reason our spam filters and recommendation engines actually work.
I think it really all comes down to this. A model that hasn't been validated is just an opinion. It's a black box making claims that we have no reason to believe. But a model that has been properly validated, that's not an opinion anymore. That's a tool. A powerful, reliable tool that we can use to make better decisions. And really, that's the whole point.